Welcome to Spring LIB.
Okay, in this problem, we are going to be looking at the gamma factor and how it changes with the velocity of the object we're considering. Gamma is seen extensively in special relativity, and it roughly indicates the strength of relativistic effects we would expect to see. It is a dimensionless number, meaning it has no units, and it can vary between some minimum value and some maximum value. As gamma increases, the strength of relativistic effects will increase. So we are asked to plot gamma for various values of v, ranging from 1% of the speed of light to 99% of the speed of light. And as a rule of thumb, we usually approximate the speed of light as 3 times 10 to the 8 meters per second. And that's a pretty good approximation. Now, in this problem, we're going to be extensively using a calculator to obtain our results. And all of the answers are in terms of c, for example, 0.01 c. For that reason, we actually won't need to use the value of c because it will divide out. So let's look at this, at how gamma is defined. 1 over the square root of 1 minus v squared over c squared. We see that for any v we insert, it'll be divided by c squared, so it'll lose its units. Meters per second will fall out. Thus, gamma is a dimensionless number, as we mentioned. So to start us off, we can look at the two limiting cases when v is at its very, very minimum possible, v equals 0, and when v is at its maximum possible, the speed of light. So starting with v equals 0 and plugging it into our formula for gamma, we can already see that the term in the denominator is going to simply be 1 minus 0. Thus, our answer will be 1. So this is the minimum value that gamma can possibly be. So in the case where gamma is equal to 1, we would expect to see no relativistic effects at all. So we can place that on our graph. That's going to be our floor, our very minimum possible value. Now let's look at what happens when we use c for v. In other words, when the velocity is at its maximum possible value. In this limiting case, gamma is 1 over the square root of 1 minus c squared over c squared, which will just be 1. So we actually see something kind of interesting here. We end up with 1 over 0, which is effectively infinity. You can say it's infinity. So the behavior of gamma as v increases is that it eventually blows up at v equal to c. So we can't even place that on our graph. So for all of these non-limiting cases, all the values that we're going to be using, I'm going to be using a calculator because they're not going to result in simple fractions or things that we can easily compute by hand. So I'm going to start with a value in the middle and start working my way to the left and to the right of that value. I'm going to pick when gamma is 1/2 of c. So I'm going to place that on my graph, this middle point, which is somewhere between 1 and infinity. So it gives us a lot of options. Okay, plugging it into my calculator, we get gamma equal to 1.15. Okay, so somewhere around 1. I think it might actually be better to choose a point close to c so we can try to get a maximum value and get some scale for our graph. So I'm going to pick the largest possible option that they've given us, velocity equal to 99% of the speed of light, or 0.99 c. Plugging that in. So that's somewhere around here then, really close to c. Okay, we get a result of gamma equal to 7.08. So we can use that as our scale. We'll put that right here. Say, call this 7. So for this value, we have something a little higher than 7, so let's put that on our plot. Okay. And so now that we have a scale established, we can now actually put our point for 0.5c, 50% of the speed of light, which, as you recall, was a little bit over 1.15, that would appear somewhere right here on our graph. Okay, so let's start working our way between half C and C. We already did 0.99. Let's try 0.95, or 95% of the speed of light. Okay, we get 3.2 approximately. So you see that just going 10% less than the speed of light, somewhere really close to C, the answer drops considerably. So it's gone from infinity at C all the way down to 3 within 5%. Just kind of interesting. So that point would perhaps appear somewhere around here. What about 0.90 C, or 90% of the speed of light? We have 2.29 for gamma. So that would appear maybe something like this. And as you can see, a trend is developing that we have some nonlinear concave up function. For 80% of the speed of light, we have 1.66, maybe somewhere around here. For 70% of the speed of light, we have 1.4. For 60% of the speed of light, we have 1.25. So of course, this plot is not entirely exact. We'd have to actually do it if we had graphing paper to get a really, really good result. And it would probably be best to simply plot this function in some external plotting software like perhaps Mathematica or Wolfram Alpha. But you can see the overall trend that we have some concave up, apparently monotonically increasing function. Filling in the rest of these values, slightly less than 50% of speed of light. Let's try 40% of the speed of light, 1.09. So we would expect these all to be decreasing down to 1 because that's the limiting case. 30% of the speed of light gives us 1.048. So at this point, our values are going to be extremely close to 1. At 20% of the speed, I have 1.02. At 10% of the speed of light, we have 1.005. So now we're getting so close that it would not even be very apparent on a graph. At 5% of the speed of light, 1.001. And I'm sure you know where this is going. Finally, by 1% of the speed of light, we end up with a result 1.00005. So that's 1.4 zeros, 4 zeros in a row, 5, all the way right here. So at this point, that would be virtually indistinguishable from a graph. So you can clearly connect the dots here. You can see what this function is going to look like. And the important part is that you see that once you get within 10% less than the speed of light, so maybe you're 90% of the speed of light, this is where gamma really starts to increase considerably. And this actually tells us a lot about special relativity and where it's going to be applicable. We see that really the only time when gamma becomes very large is when you're within a very, very significant fraction of the speed of light. And that might be worth considering in future examples in special relativity. Thank you.